Today we'll talk about final FPGA project. In this project there are two parts, uh, FPGA part and the HPS part. I will be talking about the FPGA part. So basically what it does is it takes a 128 bit key generated from HPS, and then it also takes 128 bit plain text which is our input, and our FPGA will encrypt the plain text using this key and gives back 128 bit ciphertext to the HPS. And my friend will talk about the HPS part. So let's see our Verilog code, and we have modified this code according to the project, and you can see here we have removed all the PIO blocks and added our block. So let's see how we have connected our ports. So in here I have added AES 128 accelerator, and in this I have added Avalon memory mapped slave bit and connected to the master, and the clock and reset is connected to the system. Here in this address map you can see we have assigned 8002 80FF address to this. So let's see our advanced encryption standard Verilog code. So here this you can see we have assigned the slave bits and registers, helper functions, and here it will take the inputs. This is the encryption method, and then last it will also have a round which will tell us at what round we are in, and then it will send it to the HPS. This is my compilation report. Here you can see the number of ALMs needed, ALUTs used, and logic registers, and the input output pins are 368, and no DSP blocks is used, and one DLL is used. So let's see our delay. Here you can see that my delay is 24.633 nanoseconds. So now let's dump our SOF file onto the FPGA board. Here, change file. This is my SOF file. Open. Click program configure and click on start. So this is successfully completed, and the remaining part of the project will be explained by my friend Suchit.
Hi, in this part, I'm going to explain What I do on the HPS side after the FPGA is programmed with the quartus.sof file, which was done by my teammate Kirtana. And I'll also explain how my HPS-C program communicates with the Advanced Encryption Standard 128, that is the AES 128 hardware accelerator, and verifies the output. First, the FPGA design contains an AES 128 accelerator module connected inside Platform Designer as an Avalon sleeve. In the address map, the AES accelerator is mapped at base address 0x8000 on the lightweight HPS to FPGA bridge. That's important because from Linux, the physical base address for the lightweight bridge is 0xFF2000. So the AES peripheral address is accessed from that plus the base address, which is 0FF208000. After programming the FPGA, I boot Linux on DE1 SoC. I copy my compiled HPS application binary onto a USB drive and run it on the board. The executable is built from AES.C using the ARM cross compiler, producing AES demo. Now I'll explain what the HPS program does step by step. When I run the .aes ./aes underscore demo, which is generated by the make command in the embedded shell uh, command prompt, the program first generates a random 128-bit AES key. It tries to use urandom, so the key is truly random. If that's not available, it falls back to the normal seed. This key is what will be used for both software and hardware encryption and for software decryption. Next, the program asks me to enter a plain string up to 15 ASCII characters. AES 128 operates on exactly 16 bytes, so if I enter fewer than 16 characters, the remaining bytes are padded with 0. The program then packs the 16 plain text bytes into four 32-bit words because on both HPS register interface and the accelerator register map use 32-bit transfers. After preparing the key and plain text, the program performs software encryption. First, the software AES implementation is used as the golden reference. Internally, software encryption does key expansion to produce the AES round keys and then runs the AES 128 cipher for 10 rounds. Each round includes sub-byte shift rows mixed columns for rounds 1 through 9, and then the final round does sub-byte shift rows and adds round key without the mixed columns. The result of this step is the cipher text produced by the software. Then program performs hardware encryption using the FPGA accelerator. This is the key part showing HPS to FPGA communication. The code opens the dev mem and uses mapping to map the lightweight bridge address space starting from 0xFF2 00000 into the process address space. Once it is mapped, it creates a pointer to the AES accelerator registers by adding the accelerator's QSys base offset, which is 0x8000. Now the registers protocol is simple. It writes the 128-bit key into the key registers, key 0 to key 3. It writes 128-bit plain text into PT0 and PT to PT3. It writes 1 to the control register, which asserts the start bit. Then it then it pulls the status register until the done bit becomes 1. When done is asserted, it reads back the ciphertext CT0 to CT3. So at this point, I have two ciphertexts, the ciphertext from the software AES and the ciphertext produced by FPGA accelerator. After that, to satisfy the software should encrypt and decrypt requirement, the program also performs software AES decrypt, which can be seen here from this rubric. It takes the ciphertext, uses the same 128-bit key, and runs the AES inverse cipher in software that includes the inverse operations in invert shift rows, invert sub-bytes, add round key, and invert mixed columns for the appropriate rounds. After decryption, it produces a recovered plain text. Finally, the program does a second correctness checks. It compares the decrypted plain text against the original plain text I entered. If they match, it prints a second pass that confirms the software AES implementation is consistent and the entire encryption decryption chain is correct. In the printed output, plain text key, ciphertext, and decrypted plain text are displayed in hexadecimal. That's expected because internally AES works on bytes and hex is the standard way to show 128-bit values. So to summarize the full HPS flow, I run the program. It takes the plain text input, generates a random key, computes software AES encryption as reference, sends the same plain text and key to the FPGA hardware through LW bridge registers, wait for the run flag, reach the FPGA ciphertext, compares software and FPGA outputs, and finally performs software decryption and confirms the plain text is recovered. When both comparisons pass, it proves that the FPGA accelerator and the HPS software are correct and consistent. Let me also show you how the make files were created. So after opening the embedded command shell script, I've gone into the folder where I've created the HPSC files, and then I run the make clean and make commands to get the required AES demo file, which I'll be dumping into my pen drive. And also the Linux part was implemented using a software called as Terraterm 5. This software was installed, and after that, we used a driver installation to update the COM ports and use this as a serial port. Now you can see here we had make file and the AESC file. Using this, we created the HPS file and the AES.o file and the AES demo file, which was eventually dumped onto the pen drive and connected to the FPGA board, which was used in the Linux terminal to get the desired output. We are implementing a real AES 128 accelerator in FPGA using Avalon MM. The HPS writes the plain text and key through the lightweight AXI bridge. The FPGA performs AES encryption in hardware and signals completion. The cipher text exactly matches a software AES reference. I have done all the Linux commands and implemented the final project here. As you can see, after giving the ./AES demo code, you can see that it's asking for a plain text from the user, which I've given my name, Suchit, and then it takes the plain text from ASCII to numeric, and then it generates a 128-bit random key, which then goes to the FPGA board, and then the FPGA board gives a ciphertext using the key, and also the software side HPS also gives a ciphertext, and you can see both these ciphertexts match and the result is given as pass. And you can see the plain text decryption from the HPS software side as well. It matches the original plain text. This indicates that we are getting the desired output. Thank you.